In this video, we're going to discuss how to calculate the residual strain in a material that is loaded into the plastic regime and then unloaded. And we're going to use a linearly elastic, perfectly plastic model. So to start, let's go ahead and put out the beginning of a stress-strain curve. So we have stress on the y-axis and strain on the x-axis. And we're told that there is an elastic modulus of 126 gigapascals. So we realize that for this portion of the stress-strain curve, it's going to behave in linear fashion, and it has a slope with elastic modulus of 126 gigapascals. Now, the expression that we use to describe this behavior is Hooke's law, so sigma equals E epsilon. And we can go up to a certain point where we have a yield strength. They tell us, or I've written out, that the yield strength is 170 megapascals. So once we get to this point, we cease to be acting in the linear regime, and it is often useful not only to think about the yield strength of the material, but also to think about the yield strain that might be associated with getting to this point of yielding. So once we've kind of put that out there, we realize that we're going to just stay flat and horizontal after we get to the yield strength. This is a linearly elastic, perfectly plastic model after all. Now, to calculate the residual, or not the residual, to calculate the yield strain, we can reorganize the equation for Hooke's law and realize that we substitute in the yield strength for this sigma right here, divide by the elastic modulus, and we're left with the yield strain. The yield strain can be calculated then from the values given. We have an elastic modulus of 126 gigapascals that goes in the denominator, and a yield strength of 170 megapascals. So to calculate out what this yield strain is, we can do it a couple of different ways, but we'll go ahead and just do it quickly in Google. And we've got 170 megapascals divided by, and you can see I've already kind of done this, okay, like that. And it's 1/1000th and a little bit more. And we can say in percent, and that will get us to 0.135%. So we go back. Often, we wait till the end to calculate numerical values in this class. We try to do as much as we can algebraically, but in this instance, it kind of makes sense to perform this intermediate calculation, even though we're not done with the whole problem, or while we're not done with the whole problem. Okay. So we've calculated out what this yield strain is associated with the yield strength and the elastic modulus. What's next? Well, we're going to load up to 0.3%. So that's significantly more than 0.14%, if you will. And let's just say that that gets out to some location here. We'll call that epsilon max. And we can say that epsilon max is 0.3%. Now, we're looking for the residual strain when we unload. So what does unloading look like? And then we'll calculate the residual strain. Well, unloading, as we've discussed in class, means that we go back down the elastic modulus, or with the slope of the elastic modulus. So we go back down like this. And we can think about what the strain might be associated with going back that amount. And actually, that is going to help us figure out what the residual strain is. Okay, so the residual strain is actually going to be from the origin, from where we started, to this location. And so we know that we got up to this 0.3% here, and then we went backwards. And since this line is flat, we just backtrack the same amount that you would have gone up or over, okay, to epsilon y. So this gap between here and here can just be given by epsilon y. It's now somewhat straightforward in that we have this residual strain on the bottom going to be equal to the epsilon max minus epsilon y, just like that. So if we want to go back to our Google, we could say that we have our epsilon max, which was 0.3%, minus 170 megapascals divided by 126 gigapascals, just like that. And when we calculate that out, we get some small number like that, and we can type in percent again, and that's the result that we are looking for. So we have that the residual strain is 0.165%. And just in case anybody wants to spend extra time on this problem, you don't have to. But once again, we can do the calculation at this point in a Python notebook using Google Colab. And we have here that we're going to import NumPy as NP, hit Control Enter, run it, do a little more code. And we have, well, let's see, a few different parameters. We have the epsilon max, which we said was 0.3%, but really what we should do is probably just multiply that by 1 e to the minus 2. And so that just gives us unitless, okay, strain. We also have a yield strength, and that we said was going to be 170 megapascals. So once again, we probably want to just do E1, E6, and that will give us pascals. We have an elastic modulus, and that was either is equal to 126 gigapascals. So we probably want to just do 1e to the 9, oops, like that. And that will give us units in pascals. In the end, what we determined, right, is that the equation for epsilon r is going to be the epsilon max minus the sy over e. Okay, just like that. So we can do print epsilon, well, actually, let's do a little bit better. We'll do epsilon r is going to be equal to MP round. And we have epsilon r, and we'll go to, I don't know, maybe probably 4 decimal places. And, well, do we want to put it in percent? If we do that, if we want to put it in percent, then what we need to do is multiply by 100, like that. We hit enter, control enter. Oh, I guess I made a mistake. Here, yeah, it's not 17e. It's 170 times 1e6. Okay, so the residual strain ends up being 0.165%. Thank you. I hope you found this useful.